All right, so we began our study of simple harmonic motion by looking at the motion of a mass on the spring. But of course, any time you have a force that is directly proportional to the distance from equilibrium, so if we let the distance from equilibrium be represented by a variable x, if you have a restoring force, one that's back towards equilibrium, and that the force increases as you get further from equilibrium, it will always be the case that you get simple harmonic motion with the rate of vibration given by the ratio of whatever this number is to the mass. So there's a couple of other systems where that happens. For instance, let's consider the simple pendulum. Okay. Now the forces that act on it are, first of all, the gravitational force, and that'll just be straight down. And then the other force that acts on it is the chord tension, which is along the string. Now, this particle, we call it the bob of the pendulum, is going to be swinging back and forth in a circle like this. So this suggests the use of cylindrical coordinates. The radial direction this way will be outwards pointing, and then the theta direction will be the direction of increasing theta. So we can just pop those little unit vectors on there. So as defined, so this will be the radial direction here. Whoops. I just lost my unit vector. Okay. All right, good. So this will be the theta direction of increasing theta, and then this will be the radial direction right here. So we can see that we've got string tension, and we're going to have to resolve gravity into components. Now, if this angle up here is theta, as indicated, that means this angle down here is theta as well. So we've got mg cosine theta there, minus tension, those would be the radial forces, and then we've got mg sine theta in the negative theta direction. So a reminder of our kinematics in cylindrical coordinates. Sorry, I might have been calling the polar coordinates, but really it's cylindrical, it's r theta z. And now we can write out our force equations. So in the radial direction, we had an outwards mg cos theta, that's the positive real direction. Then we had an inwards tension, and that's got to equal the mass times the radial acceleration, because that's the net radial force. Then in the theta direction, we had mg sine theta in the negative theta direction, so that's got to equal the mass times the theta acceleration. Now, if we take this equation here, we can see we can cancel the masses, and that gives us a theta acceleration of g sine theta. But of course, the theta acceleration is m. The radius is constant on the pendulum and is just given by the length L, right? And so r dot will be 0 in that case. So this term of the theta acceleration just disappears, and we end up with L theta double dot. So now let's take that equation. We can cancel off an m. We can divide by L, and we get something that looks a lot like, a lot like simple harmonic motion. So what we've got then is we've got theta double dot equals minus g over L times sine theta. So remember, for SHM, it was like x double dot is minus k over m times x, and that was the equation we solved and got cosines and sines. It's almost like that here, except we have sine theta instead of theta. Well, in the small angle approximation, for very small angles, because of the Taylor series for sine, at very small angles, sine of theta is approximately equal to theta. So we can, as long as we're dealing with small pendulum motion, replace sine theta with theta, and then we do indeed get simple harmonic motion. We get the same differential equation we had earlier. So in the small angle approximation, where we had theta here, sine theta, it becomes theta, and then we get this equation here. Now, if we define omega naught is this constant, then we can see that the function that is its own second derivative will be something like a magnitude times a cosine of omega naught t, where this is the omega naught. So just by comparing with what we had earlier, we can see that we're going to get a very similar solution. Now this function x indicated the position of a particle going back and forth in simple harmonic motion. This is going to indicate the angle of the pendulum as it swings back and forth in simple harmonic motion. So this angle is going to go back and forth like that, and it will keep the same amplitude as long as there's no damping. So this is, of course, just one solution. With differential equations, because it's second order, you need two independent solutions, so we could have cosine plus sine. We've seen previously for the mass on a spring that you can write it as cos omega t plus delta. We also saw that another way to write it is in terms of complex exponential functions. But in all cases, the rate of vibration is the root of g, the Earth's gravitational field strength, divided by the length of the pendulum cord. So as a for instance, let's say we had a pendulum with this length, and this was the mass on the end, and then we lift it up, so it's at an angle of 1/4 of a radian. Now a radian is about 60 degrees, so 1/4 of a radian is about 15 degrees. Oh, I shouldn't write that in just because that's approximate. I should write 0.25 rads there. Okay, so that's the release angle right there. And if there's no damping, then so we'll call this theta naught, and that's this initial displacement. When you let it go, it'll swing back and forth and back and forth and back and forth, reaching that same 0.25 rads on either side. Now, the radians per second of vibration will be root of g over L, so that's the root of g over 0.8. And then we can write an equation for theta as a function of time. It'll be theta naught. We'll use the cosine omega t plus delta solution. And so this is going to be 0.25 cosine root g over 0.8 t plus delta. So now at time 0, theta is the maximum value. So if you put time 0 here, excuse me, you get just the delta surviving, and so this becomes the condition, the initial condition, and then you can see that delta will be identically 0 because that gives a cosine of 1. So we write for theta as a function of time, it's 0.25 cosine root g over L times t, and that would describe the motion of this pendulum bob back and forth and back and forth and back and forth. Next, another system where we see simple harmonic motion is in the potential wells. Now we already described or discussed these, and we said that if you've got an equation for the potential energy, then in this well, if you, first of all, the mass would be at rest and this would be a stable equilibrium here, but if you gave it a little bit more energy, then the system would move back and forth between these two turning points here, and this would be your maximum kinetic energy. Up here, your kinetic energy would be 0, and it would be all potential. And so the system, you could visualize it just as a marble rolling back and forth in this bowl. Well, that sounds a little bit like simple harmonic motion. There's certainly a restoring force back to the origin. It turns out that many potentials will give you simple harmonic motion. And the way that we're going to approach this is our force function, we're going to do a Taylor expansion for it. And then we're going to do the linear approximation. So we'll drop the higher order terms in the Taylor expansion. And then if you look at this, those first two terms, this is just a constant, this is a constant, and then this is the parameter. This is how far you are from the equilibrium point right here. So we see that that looks a lot like, again, a Hooke's law force, where the force is proportional to the distance from equilibrium. And that should mean simple harmonic motion. Okay, so what we're doing here is sometimes called linearizing the force. It's taking the force that isn't really linear and just finding the leading linear term in its Taylor expansion. So here's an example here. Here is a potential well, and as x goes to infinity, it goes to 0, so it does really look like a well. And it's kind of an upside down thing like this. And And let's find the force function. We know the force will equal the negative rate of change of potential energy, i.e. the negative slope. And so consequently, when you're on this side, the force is going to be back down towards the equilibrium point down here. So we've got to do the negative derivative of x squared plus a squared to the minus 1. So the minus 1 comes down. It's x squared plus a squared to the minus 2. And then we've got to multiply by the derivative of the inside, which is 2x. And that should do it. Okay, I know what the problem was. There's an extra minus sign in the potential energy, so there's the extra minus. So now I get a minus and a minus and a minus. It's overall negative. I knew I needed that negative because for positive x, I wanted the force to be to the left, i.e. in the negative direction. So for the equilibrium points, equilibrium happens when, it's implication, equilibrium implies the force is 0. Now this denominator is never going to be 0, so the force is only going to be 0 when x is 0. And so we've got an equilibrium point at 0. From the plot of potential, we could see it's a stable equilibrium in that if we displace a little bit from the equilibrium point, we tend to come back to it. Now, the next thing we want to do is we want to linearize this force function. Okay, that means we want to do a Taylor expansion about 0. So the function f of x will be its value at 0 plus the value of the derivative at 0 times x minus 0. So the value of the function at 0, putting in 0 here, you get identically 0. That makes sense because there's no force at 0. Then we've got to do the derivative and then multiply that, put in x equals 0, and then multiply by x due to this term. So the derivative of this function, well, we're going to have to do the product rule on that. We're going to need a little bit more room for that. So we want to do the derivative of minus 2x times x squared plus a squared to the negative 2. So that'll be negative 2, doing the derivative of the first term, times that, minus 2x times negative 2. This will go to the negative third power. And then we need to multiply by the derivative of the inside, which again is going to be twice x. So this is a pretty big, messy function, but the good news is about to happen here. So this is going to be 2, 4, sorry, that's not equals, that's subtract. That's going to be 2, 4, 8, and it's going to be x squared. Oh darn, I forgot to change the pen size. Wish I could make that a default. And this is going to be over x squared plus a squared cubed. Now then, that is the derivative f prime of x, but of course we're interested in the value when x is 0. When x is 0, this whole term just gets wiped away, whoomp. And when x is 0, we end up with negative 2 over a to the 4th. And so this then is an expression for the force function when we're really close to the equilibrium point, because we've dropped all the higher order terms in the Taylor series. And that is only strictly true when you're close to that point. So we could see that it looks a lot like f equals negative kx, where the effective k value is the coefficient of x, it's minus 2, plus 2 over a to the 4. So we're comparing with the Hooke's law force, negative kx, and we see the 2 over a to the 4th is the k value. So then we know the frequency of small vibrations is the root of k over the mass of the particle. So this is the k constant. The mass we'll just leave as a variable. So it's 2 over m a to the 4th. I guess we could simplify that a bit. And this would be an expression for the frequency of small oscillations in that potential well. So that if you had, say, a particle that was displaced a bit from equilibrium, it's going to go back and forth and back and forth and back and forth. And we're saying that as long as that displacement is small, then the motion of that particle is going to be given by simple harmonic motion, like a cos omega t, and the omega is this value that we found right down here. So that's two systems where we get simple harmonic motion behavior. The pendulum, in the case of small angles, and then the potential well. Some potential wells can be linearized, and we can find the frequency of small vibration.